Welcome to a session with Carla Almeida. We're going to be talking about her paper, Analog Gravity and the Hawking Effect, Historical Perspective and Literature Review. We will be focused on the historical context of the Hawking effect and how analogies were used during this time period to develop the theory in more detail and to get deeper levels of understanding. I hope you enjoy that. Let me just kick you off with the question of what led to the publishing of the paper. Like, what's the original intention for it?
Okay, great. So my co-author, Maxime Jaquette, he saw this call of a special issue on a journal. It was a call aimed for history for physics. We should, where people should gather, physicists together with a historian to bring together one paper for the use, trying to think of how to approach history in a way that it would be useful for physicists. Maxime is a physicist. I am a physicist also, but I work with history of science, so I took over the historic part. And he invited me because I've been working with the history of black holes for quite a while. I've been wondering of the origins of the black hole idea. I worked with thermodynamics of black holes. So he invited me to research, to try to understand how analog gravity came to fruition and became this research program that it is today, which is very large. So this intended paper was to build this, try to get history to aid somehow current research on analog gravity, and I think we were successful in this enterprise, because when we started, we had no idea if we would produce something that it's like every research, right? You don't know where you're going with it, but once you arrive, you understand it better. And I think we could do something very good with history and to understand more where the research on analog gravity is going today.
Okay. Would you mind also articulating what the hope is for putting the paper out? Like, for people that would read this, is the intention that they would somehow learn in a more efficient way how to make use of analog gravity methods, or do you have a sort of articulated vision for what the paper aims to also contribute to the research space?
Yes, we discussed a lot what was the goal of the paper when approaching the subject, and our answer is philosophical. It's not for people to learn about analog gravity. It's not for a review of the technicality of analog research. It's more trying to understand how can we use analog gravity, what can we learn with it, how people used it in the past. So let me start by trying to explain what analog gravity is, right?
Yes.
So analog gravity is actually an analog experiment is when you try to replicate the conditions of a system that you do not have access within a system that you have access. So you have something that can replicate more or less, maybe more or less, analogically the conditions of the systems, the system that is inaccessible. And for us, black holes are inaccessible systems, right? We do not know, we cannot manipulate a black hole. So there's this meme that goes around the internet that says, scientists create a black hole on the laboratory and it behaves just like I don't know, Hawking predicted. And the girl in the meme goes, the what? Like the black hole on the laboratory? No, we do not create black holes, literal black holes on the laboratory. What we do is to emulate black holes on the laboratory. So it's an analog black hole. It's not the real object.
If we think about the field of analog replication in general, not just in the case of gravity now,
Yes.
but in general, so gravity is kind of like the obvious case, I think, for where you would want to do this, or at least in the case of black holes, because, well, they're clearly inaccessible and very hard to get any sort of measurements from.
Yes.
But are there any other like fields of research where this was extensively used before the case of black holes and gravity? Like, are there any, let's say, hallmark studies where analog techniques were pioneered?
Yes, since the very beginning of physics, people compare things.
Let me maybe like add to the question a little bit. I don't mean in the sense of just creating an analog system of something else, but creating an analog system of something else where you don't understand the workings of this something else in good detail. So with black holes, it's very much, at least as per my understanding, but correct me if I'm wrong here, at the time of the development here, a phenomena that wasn't very well understood and where you're not even sure what analog model to represent your black hole with. And so what I'm coming at is more that aspect of the question, that if you have a system that you really don't know how it works, you want to replicate it with some analog model, but you don't even have enough information to know what analog model to pick. Are there any other fields of research where you know about us encountering a situation like that before?
Yes, quantum mechanics. I mean, quantum mechanics is really something that was kind of in the 20th century, two theories were really revolutionary, right? It was quantum mechanics and general relativity. So this is the general relativity part of the analog experiments. When it comes to quantum mechanics, things could get really bizarre. So people often try to understand the quantum properties through analog experiments, and it can be really way more tricky to do an analog experiment with quantum mechanics than with general relativity, because general relativity is in a way classical, right? It's in the macro scale, classical in the macro scale sense. So the physics of the macro scale is more it's easier to compare two classical systems than one quantum systems and a classical system, right? But we see not a lot. I mean, analog experiments are really controversial because you can never know what to expect from it. If it works, for example, if we can replicate a black hole in the laboratory through analog gravity, for example, does this mean that the effects we observe in this analog case happens in real life, in the inaccessible system, happens with black holes? This is a philosophical question that is really controversial. People say that yes, we can learn a lot with analog gravity, and others say that it's completely useless because you cannot compare two different systems. The physics are different, so the effects are not comparable. So coming back to the goal of this paper, we did not want to answer if analog gravity is good or not to assess the vicinities of black holes. But we wanted to show that they were used this way throughout history. They were used to assess what is happening around a black hole. And that's the beauty, how we think it should be. It's not historically, cannot match how historically it was used. Does it make sense? I mean,
Well, so coming back to the philosophical point of analog models in
yes,
general, I mean, you could also make the case that all models of the universe that we have are, in some sense, analog models. I mean, they're all simplifications since we don't have a grand unified theory of everything. Um,
yeah, but it's
it's
not analog. It's not true analog. It's okay, simplification. It's we call it toy models, maybe, because we don't know everything, but it's not analogies,
So
right?
what is the okay? So maybe we can linger on that point for a second. What is the technical difference between the two? So let's say you have classical mechanics, and you tell a story about how the world works in the context of classical mechanics, which is an approximation to what really happens in some way. We don't know exactly how that is an approximation, but nevertheless, it is an approximation that seems to work well in the scale that we occupy. Is
Yes.
that not then an analog model of how the world works? Or is there a difference here that I'm
No, there's a difference. Yeah, you are describing a word, a system. So you have the natural system. If we all believe that science can replicate the natural system perfectly or not, this is another entirely philosophical question, right? It's how realist are you in your belief in science? Let's put it aside for a moment. But you have the natural world and you have a model to describe it.
Mhm.
It's not a model that is an analogy to the physical world. It's just a model that is describing it in the sense that we do not have to transpose science to another system, to another set of rules to understand it.
So, well, I'm not sure I agree, but maybe I'm missing something. So let's say you
Yes,
have some classical mechanical system and you implement a model for that in a computer,
yeah,
let's say. You're running car simulations or whatever on car crashes, and you implement it according to a physics engine that is running, let's say, classical Newtonian dynamics. And if you do that, aren't you transposing the world, which is kind of functioning according to Newtonian mechanics, but not quite? But you're imposing that onto a system or onto a model that acts exactly according to the Newtonian formalism. Isn't the model that you're considering then an analog model? I just want to make sure I
no,
understand like what we really mean when we say analog in this case.
no, simplification is not analogy. So analogy is, for example, when you compare, let's use the example that we will see later in the paper. For example, you get a black hole and say it's like a fish running through a river with supersonic speed, right?
Mm-hmm.
So you are getting the black hole, which is a system described by general relativity, by this classical gravity theory, and transposing it to a fluid mechanics system.
Mm-hmm. Mm-hmm.
You see?
Well, I mean, okay, I see the point. I see the point. I would say what my what I was trying to convey in my question is, I would say, a very subtle point. No, because if you think about Newtonian mechanics, you're saying that that is a simplification of how the world works, but you don't have any real justification for that. It's actually an accurate simplification, right? It's a story you tell that isn't a story by analogy to begin with that describes the world so well that we term it a simplification. No.
I don't see how it is an analogy. I
So
can. It's not because when you what I'm considering here analogies, right? It's not just a description of something. It's a description using completely different thinking or words or completely different example from the physics. So you have the real world and you have a system describing it. It can be simplified, okay, but it's not, you are not using an entirely different system that is apart from the nature to describe it.
Yeah.
So it's
I mean,
really
I see the
more
rationale. I
transposition.
agree with what you're saying as well. And my point is kind of a silly, subtle remark on it. We can take that up after if you want and continue it.
Yes.
I don't want to hold up too much of the interview on this point. So
You can-
let's get back on track, I think.
Yes, okay.
But we've talked about analog models now, and I think the other point that's important to consider is the Hawking effect, or just giving an overview of that. So would you mind describing briefly what that is?
So the Hawking effect, so let me say for the astrophysical effects, right, which is the Hawking radiation. So Hawking proposed that black holes should radiate, and which is something really strange, because classically we know that nothing can escape a black hole, right? So how can they radiate? So what Hawking did was to analyze the gravitational field around not inside the black hole, but around the event horizon, which is the limit where nothing can escape, and try to calculate the vacuum. Let's put it like this. The vacuum is not really a vacuum, right? We have every moment in the vacuum what you call quantum fluctuations, which is the creation and annihilation of particles. So what Hawking did was to calculate the rate of creation and annihilation particles on the very edge of the black hole. And he realized that more particle is created than annihilated. So this difference between creation and annihilation is what we call the Hawking radiation, right? So this is what we are trying to understand through analog gravity.
Can you elaborate a little bit on how the creation of these particles and antiparticles, and the fact that we have more of them created than annihilated, why that leads to the radiation as well?
Yes, sure. We have there is this particle version of this explanation, which is not very, very accurate, but let's say we have creation and annihilation is based on a pair of particles. So we have a particle and an antiparticle created, and almost instantly they annihilated each other, right? So it's a creation of a pair of particles and instant annihilation, because when you collide particles and antiparticles, they poof, disappear. So the particle explanation is that more particles escape the black holes than antiparticle. So the antiparticles are drawn inside the black hole, and the particle escapes. This interpretation, this particle interpretation, is has a bit of a problem, because why would only the antiparticles be consumed by black holes and not the particles, right? And antiparticles has negative energy, so the negative energy would be reduced from the black hole mass, and it would eventually evaporate. So this is the particle explanation. When you think of fields instead of particles, you have a field of creation and a field of annihilation. And the curvature on space-time is so extreme there that favors the field of creation. Let's put it like this. I have to say that field of creation is not a technical term. Okay, I'm just trying to explain here through analogies, but it's not a technical term. So yes, so the extreme curvature of a black hole favors somehow the creation, the field of creation, the creating particles instead of the annihilation.
Is there some intuition for that? Like, are you able to give some intuition for why that is? Or is that simply, does it simply boil down to the mathematics and you have no additional explanation for why it happens?
Yes, the intuition comes from thermodynamics, right? Have you ever heard of the black body radiation?
Yes. Yes.
So the intuition comes from the black body. It says that any body radiates by itself, not reflecting radiation, but emitting its own radiation. So when you think of a black body, it makes sense that the black hole, even if radiation cannot escape from it, matter cannot escape from it, it would have something like a black body radiation to it. Otherwise, we would have a disturbance in the thermodynamics of the universe because we have something that does not match our description of thermodynamics, right?
Okay. So maybe we can start talking about the history around these then. So I think there are 3 different sections or 3 different categories in the paper for different time periods. So if we start with maybe the formative years, if you want to give an overview of what happened during those.
Yes, of course. We identified 3 different phases for the use of analog gravity in research. And this first phase, we have something like people were trying to understand what a black hole was. Because nowadays, we get pretty good understanding of what is a black hole. We hear black holes a lot. They are in the media, they are in the memes, they are everywhere on the internet. But in the 60s, right, in 1960, black holes were very, very obscure science. There were only a few people who would work on black holes, and nobody really understood what they were. So people were trying to understand more about these objects. And it was only natural that analogies came to aid people to understand better what black holes were, right? So the first analogy we have is, let me remember, it's Zeldovich's resonator. So there's this Russian academicist called Yakov Zeldovich, Soviet, right? It was Soviet at the time. And he compared the black hole with a cylindrical resonator. And people understood how to deal with the resonator. A resonator is a classical, so it's classical. You can learn quantum effects from it also, but it's a classical experiment that people could understand how it worked. So the first analogy was Zeldovich comparing a black hole to this resonator to try to understand how could we extract energy from a black hole. Because there is this process called the Penrose process, named after Roger Penrose. to extract energy from a black hole. And Zeldovich said, well, we could think of it as a resonator, and here we can see how this could happen. It is Zeldovich was really intuitive, had a really intuitive understanding of physics, and he showed how could this happen. He by no means used this analogy to assert anything about the black hole. So it was not him trying to get proof that black holes exist. It was him trying to understand how black holes worked, right? And then there's the Unruh analogy, which is the fish in the waterfall. So this is more of a pedagogical analysis. Can you go to
the? Maybe I can scroll down. I think it's
yes.
It is here, right?
Yes, perfect. So this is the model Unruh presented. So he said that there should be, if a fish is on the on a river and it falls down on a waterfall, and the velocity of the water is greater than the velocity of sound, then if the fish screams for help, the message would not get to the fish on the top, because the water would carry the sound with it and not allow the sound to reach the external part of the river, the top part of the river. So the top of the waterfall there would be the horizon, analogous to the horizon on the black hole. The velocity of sound would be an analogy to the velocity of light, right? The speed of light.
Yep.
And the other fish falling in a waterfall would be an observer crossing the horizon inside the black hole. So this illustration, this model was proposed first as a way of teaching what a black hole was, what the horizon was, and what is the features of this very strange astrophysical object, right? So people were trying to understand what were black hole. They were building upon the theory. They were not trying to say by any means that black holes were waterfalls or were resonators. They were just trying to understand it. And then we come to the testimonial years, right? No, so we have another, I think we have another analogy, which is the thermodynamics analogy. So there was this physicist at the time. He was a doctorate student called Jacob Bekenstein, and Jacob. I think it's Jacob. Yes. He proposed that black holes were thermodynamical entities, and this was not well accepted at the time. But they accepted the analogy of black holes with thermodynamics. So this is the difference between analogy and the real deal, right? So
okay, so let me jump in here with a last shot at what I tried to make the point of in the beginning. So if we're getting a bit philosophical here for a second as well, then you have the concept of metaphysics, no? And then you have the concept of physics. And what I try to argue the point for is that physics is an analogy of metaphysics. You can interact with the metaphysics indirectly through your experiments, for example. And the world operates in some way. We don't know exactly how. We, based on our experiments, derive some stories about how the world works. And I would say all of those are per necessity analogies that might happen to actually be correct with a capital C, but we don't have any justification that they are. And so what I'm saying is, if we're talking about the definition of what an analogy really means, that's why I asked whether or not all models that we have of the universe are analogies in some sense, because we have no justification that they actually represent the metaphysics in question. Is it?
I guess.
So it's kind of a silly point in a way.
Yes.
But that's anyway. I think that's a bit clearer explanation as to what I tried to get to before.
Yes, no, but this is it's not silly. It's philosophical, right? Philosophy and metaphysics, they love metaphysics. So you have a point. Philosophically, it makes sense, but it's not the kind of analogy I'm dealing with here. Right?
Okay.
So
yes.
This is, analogies, I'm really comparing two different systems, not just physics to metaphysics in the sense. But yes, now I got your point better.
Yes. Okay, but it's in the context of the paper, it's still kind of silly. So let's transition to the testimonial years then, and then see what happens there.
Yes, exactly. So it's a good thing that Bekenstein said that black holes were thermodynamical entities, but the whole community disagreed at the time. So they said, no, it's not a thermodynamical entity because it does not radiate, it does not have a temperature, it is not a thermodynamical entity. But we can get useful information on black holes using an analogy with a thermodynamical, with thermodynamics. So Stephen Hawking, Brandon Carter, and John Bardeen, they wrote a paper with the 4 laws of black hole mechanics, which was an analogy to the 4 laws of thermodynamics. And then they got a lot of information on black holes with this analogy. And then when Zeldovich proposed this other let me say, in 1974, Hawking was visiting Zeldovich and his student Alexei Starobinsky, who have recently passed. And Zeldovich and Starobinsky told Hawking about the quantum effects around the resonator that should be comparable to the black hole. And so Hawking did this calculation, and he realized that black holes have radiation. This should radiate, not because matter is escaping the horizon, but matter is being created in the vacuum around the horizon, while the antimatter is being absorbed, right? And then Hawking said, well, now black holes radiate, so they do have a temperature, and they are in fact the closest in nature we have to a black body. And then the once analogy became not an analogy, so we could use thermodynamics effectively within the physics of black holes, right? So it ceased to be an analogy because now it's the primary physics of black hole. But then another analogy came to fruition based on this fish in the waterfall model. Because once it was thought to be pedagogical, right? Who wanted to teach about black hole, but then he realized, well, maybe there's more to it than just a silly analogy to explain what a black hole is. So he did the calculations and realized that the motion of the fluid, of a supersonic fluid, would be equivalent of the motion of space-time around a black hole. So this equivalence is an analogy, right? Because you're trying to compare a system of which is not based on fluid mechanics, which is gravity behaving
Yeah.
around
No.
black
The
hole.
fact that it is an analogy is perfectly clear. What I'm thinking of now as we speak is whether or not like you have any the way you construct your analogy in such fundamental cases as with gravity, for example. It's something that we don't necessarily have intuition for. I mean, we do have intuition for gravity on the scales that we
Yes.
occupy, let's say, but as a general physical phenomena, we don't really have any reliable intuition for it. So it's interesting to me the process for establishing these analogies. I don't know if you're aware of any ways that that is generally speaking approached, like
Generally speaking, sorry.
more approached. So like let's say as we're trying to understand new phenomena, like similar to these black holes, the choice of an analogy in your model is, I guess this is the point you were alluding to before, to a large extent arbitrary. If your intuition is no longer suitable for that realm, and maybe gravity you could argue that it is, but with quantum mechanics for sure I would say it's not. And then nevertheless you have to impose some kind of analogy onto the system. It's a big question how you do that. If we take it back to the resonator that you mentioned before and the criticism of treating this as a thermodynamical concept to begin with, that's kind of the heart of the issue, no? Because we have an analogy that we impose and people are reluctant toward the analogy largely based on intuition, I would argue. Like I don't know why there were that, but I would venture to believe that it's intuition based where that criticism is coming from. But then you have the question of why is your intuition even applicable to this domain?
Well, because physicists are intuitive people.
Yes, that's true.
A lot of physics is based on intuition, and you've seen a lot of and physics intuition is based on symmetry, right? So the whole from what I gather from history, the whole intuition of a physicist's intuition is based on how symmetry works, or how he understands symmetries, or she understands symmetry, right? Because we've seen a lot of people trying to argue against or pro something solely based on intuition. For example, Einstein never believed black hole was real. Black holes existed because he said it would be very, very ugly to have singularities on his space-time, to have this point where space-time is poked, it's torn.
Well, so, even more fundamentally than that, maybe, or as an even bigger problem, you have the quote of the God not playing dice, no? In the context of quantum mechanics, also from Einstein.
Yes, but
and I think that one is even more illustrative of the issue I'm trying to raise, because it's one thing to have an intuition for the symmetries or the mathematics associated with something. I mean, if you look at a type of problem long enough, you can build up an intuition for the equations associated with it and what you would expect from the equations. But that kind of intuition is like different from the intuition that... Yes. And the kind of intuition that you get from operating with a set of equations or something like that is fundamentally different from the intuition you have as a let's say as an object existing in the world, if you get what I'm saying. And with quantum mechanics, you might be able to build up an intuition over time for the equations, but before the equations exist to describe the system, what you're left with is an intuition of being, let's say, a human being at the scale that we operate. And then it becomes very difficult to say what analogy would even be appropriate for that kind of system.
And this is what ties science to the cultural environment the physicist is in, right? Because our intuition depends a lot on our political context, or cultural context, or philosophical background, and learning history, I've realized that this impacted a lot on the decisions and the intuitions of physicists on what to believe and what to believe, for example. One aspect that we learn with this paper in particular is that pedagogical analogies can become something more in the future. So forget about the fish in the waterfalls. We can think about the dual nature of light with the double slit experiment, right? We can see how waves behave with the double slit experiment with a water cube, right?
Yeah.
You can do it with water and exemplify how light would behave the same way if both slits were open. So this is a pedagogical experiment, but it becomes later, and not later, but almost at the same time, is official experiment, because the double slit experiment is a basic experiment in quantum mechanics, right? But we can use it for pedagogical purposes as well.
Yes. Yes.
And it happens here also with a black hole.
I see we only have a few minutes left,
Yes.
so I think we should start closing a little bit. But we didn't discuss the entire history of this. I don't know if you want to give a very short, or depending on how much time you have, more or less short overview of the last part, or whether you would just like to wrap up with a few conclusions of the main takeaways from the paper.
No, I can get you an overview of the last part. So we have these formative years where analogies were used as trying to understand the idea, and then the testimonial years where analogies were used to give more substance to the theory, to kind of establish the theory as correct. And then the empirical years when people try to build experiments to prove the theory. And this is the tricky part. If it proves something or not is kind of a debate. But this is what people are trying to do, to prove the Hawking, that black holes radiate through the analogous cases, right? So this is the empirical years, the attempt of building black holes on laboratory through analog experiments to confirm that the Hawking radiation exists, or that the Zeldovich effect exists, or the Onwu effect exists, right? And now we are seeing, this is one of the conclusions of the paper. We are now seeing the inverse. We are now leaving this idea behind that analog experiments should provide any testimony to the theory, because we are discovering new phenomena on the quantum field theory, on the condensed matter theory, through analog gravity. So we are not only trying to understand black holes, but we are using these analogies to discover new phenomena that we never even thought could happen, right? So this new branch of the analog gravity research, we called it this autonomous phase, because we do not have to justify our research on analog gravity as a way to prove something about black hole, but we can justify it by saying that we are discovering new phenomena on condensed matter, or optics, or fluid mechanics, which are the most basic analog experiments out there. So this is the paper we try to build a history and kind of but point to this new role of an analog gravity that's not connected to trying to understand the physics, the astrophysics system, but to understand better the analog systems.
Right. Very good. Maybe if there were any final words of, that you would like to share with the community, if there's any takeaways from your side from the paper beyond the let's say summary of it that you would like people to know, or anything else to the people listening.
Yes. First of all, I condensed a lot here. So if you want a better understanding, you can read the paper. It's not very technical, so even if you're not into this part of physics, you can understand how to use how analog gravity works in this case. And I honestly hope that it can be useful for physics today, because this is the goal, right? To make history useful for physics, for current physics. So yeah.
Wonderful. Thank you so much for taking the time.
Yeah, thank you once again, Nick.